Now I'd like to introduce our IFORS president, Grazia Speranza, who will begin the webinar.
Thank you very much, Mary, for the opening of this webinar. And I would like, first of all, to welcome all of you for being here and sharing with us this very important event. IFORS is very glad to host today the 5th global webinar dedicated to operations research in Africa. And as you can see, the title is Promising Developments. IFORS is the mother, as we say, of all the operational research societies in the world. It has 54 member societies, and almost every year there is some new members. The global WAR community is constantly growing. The member societies are organized at present in 4 regional groupings, one dedicated to North America, NORAM, one dedicated to the Latin America, ALIO, to Europe, EURO, and one to Asia, IFORS. And as you can see, over Africa, we have the name AFROS in parentheses, because the official groupings are just 4 at the moment. And the African member societies at the moment belong to the grouping of Euro. And one of the reasons why we decided to have this webinar today is to give more visibility to the African community, with the scope in the near future to create a new regional grouping. Please, next slide. Thank you. Before moving towards our global webinar of today, let me remind all of you that in August this year, the triennial IFORS conference will be held. The conference was planned originally for last year in June, but due to the pandemic, we had to move the conference to this year. And we hoped until the beginning of this year to have the conference in person, but again, the situation is such that we will have a virtual conference for all except those living in Korea. In any case, I would encourage you to submit your abstract to this conference. It's really an interesting, exciting conference, although it will remain a virtual conference, as I said. Just a few words about the way IFORS is organized and managed. IFORS has an administrative committee, which includes, besides me, the vice president, as you can see, the past president, the treasurer, and 4 vice presidents, each representing one of the regional groupings that I mentioned earlier. And the first webinars that we had have been dedicated to one of each region, one of the regions. In fact, we started planning these global webinars due to the fact that we did not have last year any opportunity to meet in person. The conference was canceled. And we decided to organize these global webinars to keep connected, to remain in contact, and also as an opportunity to get to know each other better. Where by each other, I mean each region of the world, from North America to South America, to Europe, Asia, and today, Africa. I mentioned that we had already 4 global webinars, one dedicated to ALIO, one to IFORS, one to Euro, one to NORAM. We had a global webinar, one every 2 months. And you can find the recordings of the previous webinars on the IFORS website. Next slide, please. So it's my pleasure today to introduce Haytham Asri, who is the president of IFORS, and he will give an introduction of the IFORS community. Thank you very much, Haytham, for being here today. Please.
Thank you. Thank you very much. Thank you for all those who are attending today's webinar. It's a great opportunity for Africa and for IFORS that we are here today to talk about something that is going on in Africa in order that we can promote operation research. Our target, as I mentioned, that we are aiming to promote OR in Africa, but we are trying to promote OR in Africa through what we call creating the network. We believe that without network, it will not work. And that's why we are trying to get all best practices in order to create the bridge between all African countries, with the aim that soon or medium term, that we will be recognized by IFORS as the main contributor for Africa in terms of promoting OR and benefit to our countries. We have a wonderful team, the executive committee. We have our past president, Charles from Kenya. We have Bernie from South Africa. We have Serine from Senegal, Fouad and Taysir from Tunisia. We have with us also Dave from South Africa. He's the president of the South African Society, and we have three societies also. Phillips from Nigeria informed, and these are the three societies that are the pillar of this. With us, we have Hans. He has long experience with IFORS and in Africa, and he dreams about the OR in Africa, one of the dreamer. And also we have Sue with us. He's our executive committee action manager. I would like to share also the goals. The goals of Africa, it's just to create what we call a network. And we took the best practices on that regard. We look at our neighbors, Euro, and we took their experience in creating what we call working groups. And I'm happy to say that today we are having a healthcare system, agri-food, MCDM, efficiency and productivity analysis from Mauritania, routing and logistics from Tunisia, meta-heuristics from Algeria, agri-food from Kenya. Then we started this experience of creating working groups and putting African researchers together. But also because we know that we cannot be recognized by IFORS unless we have a good number of national societies. And because we know that creating a national society, it's not an easy task. That's why we went through an initiative to create what we call chapters. These chapters now, they are covering all the colors you see in the map. These are the chapters that we are now handling, or we are now monitoring and giving support in order that we have chapters in Algeria, Morocco, Egypt, Tanzania, Uganda, South Sudan, Benin, Senegal, and other countries. Then these chapters, the idea is that these 8 chapters that we have now for the moment, these are really, really a good promise to be a society. And I think that soon Morocco, Benin, and Kenya, they will be submitting their affiliation to IFORS. For sure, we are very inclusive, and we are looking for all other OR societies. And there is one wonderful OR society, ORPA, another one very active in Tunisia also, TEDAS and Decision Sciences, and another one in Kenya and in Eastern Africa, ORCIA. It's kind of union of national chapters in Kenya, as I said, Uganda, etc. Then we would like to consider them. We are considering them as associate members, plus one also in Nigeria. Then this is the map. If you can go next. As you know, what is the potential of OR in Africa? And here I would like to mention that, sure, we are contributing by only 2% of the OR publication during the past, let's say, 30 years. But a lot of African countries, they have the potential to be there. South Africa, more than 50 years, Egypt, Tunisia, Morocco, Algeria, Nigeria, Kenya, Ghana, Ethiopia. These are really good. They have good centers and good researchers, and this must be reflected in the OR map. Africa has by far the strongest growing scientific production according to Elsevier. We are publishing, we are trying to publish because we have the under 20 population. 1/5 of the world youth populations are African. Then African could be the next researchers in OR that will travel, that they need to travel maybe to other countries, but we would like to create this bridge. We would like through IFORS and through the working groups and through the chapters offer more visibility for that. And I think that Africa would benefit a lot of the pandemic crisis as we are moving to online access to education and research. Today, I'm sure that a lot of Africans, they are attending this meeting remotely, and if we can ask them to move to another country to attend face-to-face, it will be really difficult. Plus, there is a fast growing of several African countries in terms of using data, using analytics in order to solve problems. And I think that by facilitating the collaboration and knowledge exchange between African researchers with their colleagues in America and Europe and other regions, all right, this will help to increase the number of OR researchers in the world and will have a better impact on the OR world. Really, we are keen next. We are keen also to have our conference, and just to show you that our conference for this year, for 2021, this conference will be in a hybrid mode. It means that those who are from South Africa, and it comes while we are celebrating 50 years of war in Africa and mainly in South Africa. 50 years, 50. Yani it shows a long history of war in Africa. It's not just we are today, IFORS, maybe it's new, 3 or 4 years, but war is there since 50 years now in Africa. We are jointly organizing IFORS 2021 with the 5th ORSA conference, annual conference. It will be in South Africa. We are looking forward to receiving your abstracts. All right, before 2nd of August, I am keen to announce that all our member society chapters working group will be there, and there you will see the potential of Africa. Just to show that before this conference, we organized another conference in 2018, and thanks to the support of Euro IFORS, we were able to sponsor 75 students to attend this conference from all Africa, and we have published the results in Springer, Wiley, special issues, and also a book. And this is because of the efforts of all those who contributed to this. Then we did one step. This was our kickoff meeting in 2018, and now we are having another milestones 2021, where IFORS will go to the international level. We are looking forward to participating, to participate, to join us. We have made, thank you to ORSA and thank you to our sponsor, the registration fees are very low, and we are happy to offer free registration to all people from developing countries. The most important is that in Africa, we believe on network, and without network, it will work, and you are going to make the network, and you are going to make it happen. That's the story of IFORS. I will be happy that you will join us, and a lot of you, please don't hesitate to send an email to one of our executive members. I will be happy also to receive your email. And now I will hand to Sue. She's a member of the executive committee to show you the panel of speakers that we have brought today, young, with a lot of expectation and with a lot of, inshallah, future. Thank you very much for attending. Sue, floor is yours.
Thank you very much, Hassan. Hey, Tim. Hello and welcome everybody. My name's Sue Merchant, as you've just heard, and it's with my hats on as a member of IFORS Developing Countries Committee and also IFORS Executive Committee that I have the very happy task of introducing today's speakers. I've been working closely with a number of African colleagues for some years now to help encourage the development of IFORS, and I'm delighted that it has recently taken several leaps forward, as you've just heard, under its president, Haytham Masri, with the help of IFORS Executive Committee members and IFORS. It's therefore a very great pleasure for me to welcome participants to this 5th webinar in the series, which includes 3 talks from African researchers from the south, west and north of the continent, and demonstrates the wide range of OR taking place there. I'll shortly have the delightful task of introducing each of our speakers to you in turn, but I just want to remind you about questions, please, as Mary did. The speakers will have about 20 minutes each to present, and when all 3 have finished their talks, we will have a short Q&A session. So do send your questions in by the Q&A button, not the chat button. And if we don't have time for them all, the speakers will be very happy for you to contact them afterwards. So our first speaker today, Dr. Georgina Rakotonirainy, is originally from Madagascar, but she now lives in South Africa, where she studied for the last 7 years. She successfully completed her PhD in 2018 at the Industrial Engineering Department at Stellenbosch University, and now lectures at the Statistical Sciences Department, University of Cape Town. She's especially interested in OR methods, which is wonderful, and her main application areas are cutting and packing problems. Georgina is going to tell us today about her prize-winning project on designing optimal electricity power outage schedules, taking fairness to customers into account. Georgina, the floor is yours.
Hi, everyone. It's a great honor and privilege to be invited and give this talk. I will be speaking about our work around load shedding or power outage scheduling problem. I'd like to note that this work was investigated in 2015, a year when South Africa experienced the second period of power shortages after a collapse of one of coal storage silos, which caused the shutdown of one of its largest plants. I'd also like to thank my 2 colleagues, Jan Dulba and Chua Mirinda, for their contributions in this work. Whenever there is insufficient power to supply demand, a planned and controlled load shedding is necessary. Parts of the network are switched off according to a load shedding schedule to protect the power system from total blackout. This diagram here illustrates the load shedding process for the case of South Africa. The power system is referred to as in a tight supply when all units are used at full capacity and all available reserves have been used while the high demand is not satisfied. And in this emergency state, to help balance demand and supply, demand reduction from voluntary or contracted customers are called on to decrease their demand, and that's referred to load reduction. When these 2 steps have been depleted to restore the power stability, load shedding is processed to prevent the network from collapse. And this process is executed in stages depending on the severity of the system state. For example, in stage 2, 10% of the national load, or about 2,000 megawatt, must be scheduled to be shed. In case all of these measures are insufficient, the system blackout will happen, and that must be avoided. In a case where load shedding is necessary, schedules are built in advance to indicate which areas are to be shed in each time and this load. And these schedules are published in different media to make customers aware of their possible time of shedding. And an example of a daily schedule for the city of Cape Town is shown here in this table. On the top row, we have the various time slots, and on the first column, we have the stages. And the number inside the table indicates the areas to be shed, and people know the area number by means of a map that is published in advance. So given this background and the problem in context, what we were trying to achieve in this work was to answer the following questions. The first one was, what are the various goals that play a role when designing load shedding schedules? And we considered 2 important goals. The first one is the fairness goal, which I will explain later on. And the second one is any possible impacts, and especially economic impact. Then the second question was how to generate feasible and fair load shedding schedules. And we attempted to answer these questions by developing programming models. So basically this work attempted to construct tools for supporting strategic decision-making around load shedding. So the focus was to develop programming models, which may be employed to generate feasible and fair schedules should load shedding need to be implemented. So the ultimate goals of the load shedding scheduling are to fairly allocate areas on the scheduling horizon and also to minimize possible economic impact. So basically the main objective is to emphasize the trade-off between fairness and economic cost. And defining fairness is not straightforward, but we consider two possibilities. The first one is the rotational fairness goal. This aims to avoid successive times shade of a given area during the scheduling horizon, and the cumulative fairness goal, which balances the average number of times each area is shaded during the scheduling horizon. So an example of a schedule which satisfies both rotational and cumulative fairness objectives is shown here. So in this example, all areas are shaded with the same amount of times, which is 6 times, and there is no repetition in the shading time or the slot of each area. Then we also need to consider the constraints, so the fact that the required amount of load to be shaded during each time slot must be satisfied. So given this model formulation, we consider two approaches to solve the problem. So the first one is a single objective allocation approach, as shown here. I'm not going to give details of the meaning of each notation, but I'm just going to explain the meaning of the expression of the equation. So the first expression, the objective function, number 1, represents the total economic cost. So basically the objective in this first load shedding scheduling model is to minimize the total economic cost subject to these 4 constraints. So the constraint set number 2 ensures that the required amount of load to be shared during each time slot is satisfied. The cumulative fairness is ensured by constraint set number 3. So if you look at this equation here, number 3, there is a parameter lambda, which determines the level of fairness with respect to the total number of times each area is shaded. So that is, it ensures that all areas are shaded with the same number of time periods on average. So a value of lambda equal to 1, for example, indicates that all areas should at least be shaded once during the scheduling horizon. Then the rotational fairness involves both daily and hourly allocations, and they are represented by constraint set number 4 and 5 respectively. So the daily rotation allocation constraint ensures that no area should be scheduled for shading on the same time slot over the scheduling horizon until all of our areas have been shaded in that particular slot. Analogously, the hourly allocation constraint ensures that an area should not be scheduled for shading on the same day until the remaining areas have been shaded on that day. And the level of fairness with respect to these 2 constraints is adjusted by the 2 parameters, alpha and beta. And the last constraint, number 6, ensures the feasibility of the solution. The second model is a multiple objective allocation approach, consists of a multi-objective model in which the 2 objectives, mainly the economic cost and fairness allocations, are simultaneously optimized. So more precisely, the objective function number 1, together with the set constraints 3 to 5 in the first model, are converted to a set of goals that need to be achieved simultaneously in this second model. So each goal is associated with a target value, And the objective is to minimize the weighted sum of deviation of all goals to their corresponding targets, as shown by the expression number 7 here. So this approach provides a more flexible way to model the problem, as decision maker can customize the target's value according to their preferences. And constraint number 8 ensures that the required amount of load to be shared during each time window is satisfied. Constraint set number 9 ensures that each area is at least assigned once for shading over the scheduling horizon in case there are more time slots available than areas. And constraints number 10 to 13 handle the deviation of each goal from its target value. And the last constraint ensures that feasible solutions are achieved. So these are the two approaches that we considered. In order to illustrate the working of these two models, we solved the models in the context of hypothetical data. So the data entails electricity consumption and estimated economic cost associated with load shedding for all areas in the city of Cape Town. Data on the proportion of mixed use, industrial and commercial sectors for each area is shown here in this map. And data about the population and the number of households in each area was obtained from an online source. However, data with respect to the economic cost caused by load shedding for all areas were not available. Therefore, estimated costs were employed in this work. And so these costs were calculated such that the economic costs associated with the different sectors within an area are taken into consideration. So for each area, an estimated cost was given to each of the economic sectors within the area, and the sum of these costs represent the total economic cost associated to that specific area. So this table here captures the cost of load shedding with respect to each economic sector, as mentioned earlier, all at specific time period. So we assume that these costs are the same for all areas, and these values were selected in such a way that possible significant impact and peak hours were taken into account. Measuring and interpreting the costs associated with household were more difficult than in the case of industrial, commercial, and mixed-use sectors. So in this work, we assume that the household costs are selected so that these costs neither swamp nor are swamped by the cost of the other sectors. So given this estimated cost and the surface area occupied by each sector within each area, using the data from the city of Cape Town, the economic cost associated with an area at a specific time period is determined by the formula at the bottom here in this slide. Again, the next data that required in the work was the regional electricity consumption. And unfortunately, this data was also not available. So a hypothetical case scenario was considered. So it was assumed that all areas have different electricity demand, which can be less or greater than the required amount of load to be shared with respect to each time period. And that the difference between the maximum and the minimum demand across all areas is relatively large. So that is, areas which are predominantly populated by industrial and commercial sectors were assigned higher electricity demand than the other areas, as they were expected to consume more electricity as compared to the remaining areas. And the areas were ranked based on the total surfaces occupied by the various sectors within the area, and each area was associated with a load demand that is proportional to its rank. So basically, the expected demand of an area I with a rank U is determined by the equation here at the bottom. All right, so that's the data that we considered in the work, and we can look here at the results that we obtained, first by the single objective model. So here we have the histograms of the distribution of the number of times shade of all areas when solving the single objective model for different values of the parameters lambda, alpha, and beta. So recall the parameter lambda ensures that all areas are shaded with the same number of time periods on average, and the level of fairness with respect to the daily and hourly allocation is adjusted by the parameters alpha and beta. Okay, so for a value of lambda equal to 1 and alpha and beta equal to 5, about 25% of the total number of areas are shaded more than 14 times, while 75% are shaded only once, as shown by the first histogram plot on the top left. But if the value of lambda is changed from 1 to 5, then we have the 75% of the total numbers of areas are shaded 5 times in the return schedules. That's shown in the second histogram plot on the top right. And for other values of alpha and beta, as shown by the two histograms at the bottom, the results do not change much. So the proportion of the number of areas that shade once or 5 times are still large. So these results show that there is a significant difference between the number of times each area is shaded, which may be interpreted as unfair. So the causes of this result lie in the difference in order of magnitude of all areas, as well as the cost of load shedding associated to each area. So each areas which are predominantly populated by industrial and commercial sectors were assigned with higher electricity demand than the other areas, and the cost of load shedding associated to these areas are also high. Therefore, these areas are expected to be shaded less often than the others, so that the generated schedules exhibits low cost. Okay, that only a fair schedule would be achieved with some sacrifices with respect to the total cost returned by the schedule, or in the case where all areas are assigned with identical demand. So if we assume that all areas consume the same amount of electricity at any time period, and that this electricity is equal to the required amount of load to be shared during that time period, then the first schedule may be obtained as shown here in this plot. So here we have 87% of the total number of areas are shared 5 times, while the remaining areas are shared 7 times. And then the sensitivity analysis of the results returned by the goal programming model with respect to the changes of in the preference parameters used as input of the model as shown here. So the first case study, we considered the weight associated to the economic cost goals were varied, while the other weights were kept constant. And so you can see here in the plots, the first plot, increasing the weight associated with the economic cost goal with an increasing magnitude from 1 to 7 leads to relatively small but significant decrease in the overall cost of the solution. And it results in a limited increase in the total deviation of the hourly rotational allocation goal from its target, as shown the figure on the bottom left. And then this result demonstrates that adding more weight on the cost goal enhances its importance, which results in a solution that achieves a low economic cost while sacrificing fairness allocation. And moreover, the average number of times shade of all areas is not that significantly sensitive to the changes in the weight associated with the economic cost, as shown in the box plot of the figure at the bottom right. So we can see the majority of the areas are on average shade quite frequently. Then Different results were obtained for the second case study, where the weight associated to the daily and hourly rotational location goal were varied, while keeping the remaining weight constant. So here in this case, a 64-fold increase in the weight associated to the rotational fairness goal contribute to a 15% increase in the overall cost of the solution, as shown in the figure on the top. And a significant drop in the total deviation of both the daily and hourly rotational allocation goals from their targets are found, as shown in the figure on the bottom left. These results were expected as the rotational fairness are emphasized in this case. And from the last plot on the bottom right, the schedule is notably fair as the majority of all areas are on average shared equally frequently. So in summary, all the results shown earlier show a clear trade-off between the various goals and objective functions. Although the trade-off between fairness and economic cost is a fairly obvious point, it is important because it highlights the trade-off that decision makers must necessarily confront when creating a schedule. And the results indicated that the fair schedule comes at the cost of negative economic impacts, while low economic cost requires sacrifices to the fairness of the schedule. So as a follow-up research, we acknowledge that the limitation of the work is that the models were solved in the context of a hypothetical data. So it would be good as a follow-up research to implement and assess the models on real case studies. Moreover, all parameters involved in the models were assigned deterministic values. So it would also be good to develop stochastic versions of the models. And finally, the proposed models generate schedules which only take into account future fairness. So past history concerning the allocations of areas in the past schedule was not considered. Possible future research is to develop models which are able to generate schedules that are retrospectively fair. All right, so that's it for this talk, and thank you for your attention.
Thank you very much indeed, Georgina. I think that was actually a fascinating insight into how the problems of power outage scheduling in South Africa might be tackled. Before I introduce our second speaker, just a reminder that the Q&A you might want to ask, the question you might want to ask will be held at the end of the 3 talks, but do please submit your questions using the Q&A button when you think of them and say who your question is for. Thank you very much. Our second speaker today is Jules Degila from Benin. He is senior lecturer at the University of Aborney-Calavi, having received his PhD in electrical engineering from the École Polytechnique de Montréal, Canada, in 2004. He specializes in the optimization of telecommunication networks and systems architecture, deployment, and operations. And he's led the Department of OR and Computer Science at his university's Institute of Maths and Physics, and is also the main organizer of a highly rated summer school on OR techniques and applications, which regularly gathers students, researchers, and practitioners from 11 countries from West and Central Africa. Jules has also held management, executive, and board positions for Western and African telecoms companies over the last 10 years, and is clearly a man of many parts. Jules is going to tell us today about his work on orchestrating the in-band data plane network telemetry. Over to you, Jules.
Hello, everyone. My name is Jules Degila, senior lecturer in computer science from University of Aborney-Calavi. I'm going to present you a joint work with Tiano Njai from IMSP, and Marcelo Rizeli and Luciana Burial from Brazil. So this is on orchestrating the inbound data plane network telemetry. And I would like to mention that this could be applied to any type of telecommunication network, ISP networks. So here is the agenda. After the introduction, I will run you through the concept of in-band network telemetry. Then I will introduce the problem, and we'll discuss the solving approaches that we are proposing, and then the preliminary results and conclusion, followed by some references to previous work. So network telemetry basically refers to the processes by which measurement and other data are collected about the network information, statuses, and those data are transmitted to receiving equipment for monitoring purposes. So network, the term network monitoring is new, and refers to the newer data collection and consumption techniques that we are considering in this work. So basically, you have different nodes in your networks, and then monitoring data are collected and sent to the data collector, and from the data collected can be analyzed and stored. So it's important to mention that network measurement has evolved over the time to become now network telemetry. And this picture here shows you actually, the shift in the paradigm of network measurements. Before, it was more about, using a network protocol to query equipment. So the equipment implements the SNMP protocol, for example, and it's impossible to actively collect SNMP info data, or the data can also be passively collected as well, or both, actually passive and active. But it has evolved at some point with the advances of the technologies and the computing capabilities. It was possible to separate the control plane from the data plane, meaning there is a layer, a control layer, where the measurement information, probes and measurements are performed. And this differentiates, the software-defined measurement based on the control plane from the data plane, where, the measurement information or the telemetry are collected right from the production packets, right from the production data, I would say. So the telemetry network items are embedded in band here. So, and can also be embedded out band, but along with the production data. So it can be then active or passive telemetry information as well, depending on whether nodes are actively sending the information or are being queried from time to time. And it can be the hybrid way as well. So in-band telemetry now, this is an example. The diagram here shows how the telemetry information are defined and identified, generated, and collected from the network. So let's take the example of the telemetry item 1 generated from this green node here and follows the green flows toward its destination, which is the node 4 here. So we have same thing for the telemetry item 2, but the origin is node 2 instead of node 1 in the other case. So here, for example, you know, this is a telemetry transit hop. So there is no stop at the node 5, for example. So in a nutshell, in-band network telemetry is a framework that is designed to monitor, collect, and report flows and network states by the data plane with little involvement of the control plane or no involvement of the control plane. So the idea here is to give better visibility on the network without involving the control plan and using the production data. So with that in mind, the challenges are twofold. We have to define the network, the telemetry items that are to be collected. So, consider a wide network where these items have to be collected in real time. The visibility may be degraded, depending on, how many items we are collecting, and also depending on how the network telemetry is collected as well, because monitoring applications consumes the telemetry items, and more there are, and how they are collected can also impact the performance of the monitoring application. So existing solutions so far have neglected monitoring application requirements, and with little scalability, because the number of telemetry items can grow, while in real environment actually. So it's important. I mean, in part of our program here are the monitoring applications requirements, and they are basically composed of a set of telemetry items that are to be collected for that application to perform well. And that's what we call the monitoring application requirement satisfaction. So a monitoring application requirement is satisfied when the requested telemetry items, so the subset of telemetry items, are collected from the same forwarding device so that the application can perform its functions. So this is an overview of the inputs of our problem. We have the network nodes. We also have the telemetry data that are to be collected, and they are related to the monitoring applications. So here you have the flows, you have the monitoring application, you have the telemetry data. So in this example here, we have 4 monitoring applications. And as you can see, the telemetry items are associated to the different monitoring application, meaning for M1, we need the blue and the black telemetry items. M2 only the orange telemetry items, the yellow for M3, and then the green and the red for M4. And also you can see also the path for the green, for example, it starts here and then it ends here. So we have the source and the destinations, and then the network flows will be determined So that's in the paths from the source to the destination. We also need to collect some telemetry items at specific nodes. So collecting telemetry data, and then we have to ensure that the monitoring requirements are satisfied. So we use in the attempt to, give a mathematical formulation of the problem, we use 4 types of decision variables. The first one is a binary variable, which equals to 1 if the monitoring application requirement is satisfied. So M represents the monitoring applications. D is the device where the monitoring applications data are collected, and P is actually a subset of data that are collected at that device level. So TMP represents the timing, because the telemetry item data has a timeout actually, and if the monitoring application requirement is satisfied before the timeout, it can be counted, otherwise it won't be counted. So why DVF equals to 1 when the telemetry item D is collected from device T by flow F, for example. And then we have XIJF equals to 1 if flows F go through arc IJ belonging to the set of the arcs. So we are trying to maximize the number of telemetry items that we are collecting, and we're also maximizing the timing, the time the monitoring applications are collected as well, so that the monitoring application requirement can be met. So we have a mathematical formulation of the problem. We don't have enough time to go through all the constraint, but I would like to quickly discuss some of the constraints. Each network flow starts from an origin and end and finishes at the destination. Network flows capacity is limited. Each telemetry item is collected by a single flow, and monitoring application requirements must be collected from the same forwarding device. And as I said, there is a timeout for correcting monitoring applications requirement. So as for the solution approach, so we have the mathematical formulation that we run using available software such as Cplex to obtain solutions for small size network. But we also propose an heuristic based on graphs, and with 2 main constituents, a constructive phase and the local search phase as well. So this is an overview of the algorithm that we have used in our heuristics. And we have at the input the max iteration and the data as we show in the problem. And the output will be the best solutions that maximizes, the number of collected telecommunication items, telemetry items, and also the satisfactions of the monitoring applications requirements. So the procedure is to use graphs, basically, and use the randomized initialization of the solutions, and then have a constructive phase that I will describe in the next slide, and also followed by a local search. then until we get better solutions. So for the constructive phase, we generate active network flows path from given endpoints and select an active network flows and process the devices that are on its path. And at every device, we apply an AppSac actually to determine the telemetry items that are to be collected at that path. You know, the flow has a limited capacity, so that's the size of the problem. And we repeat this again and again to maximize the number of telemetry items on every device. But this does not, you know, ensure necessarily that the monitoring application requirements are met. That's why we need the local search phase to improve actually the application's requirement. That means that the set of telemetry items, the subset that are collected at each node should be improved so that we can maximize, you know, the requirement, the monitoring applications requirements. And we can, you know, assign also new telemetry to the network flows, which still have room, and exchange telemetry items between different flows so that we can maximize the the objective. So preliminary results were derived from a network with 50 nodes, 9 telemetry items, and 3 monitoring applications. And here we can see that we collected about 140 telemetry items for, you know, 50 active network flows and so on. You know, here it's over 350 for 200 active network flows. In parallel, we have monitor satisfaction of monitor requirement here above 200 with 100 nodes. So if we come back here, it was 160 active network flows. We were able to get over 300 active monitoring requirements satisfied here. So this is how it goes. And we also run the model with, you know, the mathematical models that I put in the as backup to the slide deck. And it shows here, you know, how quicker we get the result with the model, and also how the heuristic works as well. So these are preliminary results. So we intend to improve or to increase the size of the networks and increase the size of you know, telemetry items that are being collected, and also the number of monitoring applications down the road to, you know, to see, you know, how we can actually improve our heuristics and how far we can go with the mathematical formulation of the problem. I have to say that, you know, the difference between this and what we found in the literature is that we don't determine the paths that the telemetry and network telemetry items will follow. So this is determined during the optimization. So it gives better solutions. And also, I put here some references for you. And you have as backup here the problem, the mathematical formulation of the problem. So thank you for your attention. And before I leave, I would like to quickly tell you about the school the Operation Research Techniques and Applications School for Africa that we are organizing in October 21st to 29th this year. And we are expecting about 90 people from 10 countries in sub-Saharan Africa. So you are invited as well to, submit, research, abstract papers, and e-posters as well. So thank you very much for your attention.
Our final speaker, Wassila Abdellaoui, has an MSc in Industrial Engineering from the University of Tiemcen in Algeria and is working hard towards a PhD in Industrial Engineering. She's a researcher in the Manufacturing Engineering Laboratory of the university, and she was a visiting researcher last year in the Centre of Management Studies at the University of Lisbon. She's also held internships in a variety of companies, including an Algerian company which manufactures military fabrics, a hospital maintenance service, a pipeline production company, and more recently in the oil company Naftal in Tiemcen, studying the storage and distribution of multi-petroleum products. She's also co-authored a number of scientific papers on pipeline problems, clearly a very busy lady. And she's going to present to us today an Algerian case study, that of an optimal scheduling model of a multi-product pipeline. Over to you, Wassila.
I'm pleased to be one of the speakers in the IFORS webinar. My presentation will be on the optimal scheduling of multi-products pipeline, a case study in Algeria. This work is a part of my doctoral thesis in the supervision of Professor Suyer Mehdi and Professor Sahnun Mohammed, with cooperation of Professor Fouad Ben Abdelaziz. The outline of my presentation starts with introduction and explain what means the multi-product pipeline system. Also, we present how we can do the scheduling of multi-products pipeline. We'll describe the problem and speak about our contribution, our optimization model, and in the end, we will present the case study with the result that we obtain. We conclude with some recommendation. The oil industry is one of the most important components of the world economy and has a significant impact on the development of the other industries. It plays an important role in the delivery of vital products such as gasoline, aviation fuel, diesel, and liquefied petroleum, which are used in industries and the daily life of the people. The figure shows the overview structure of the pipeline of the petroleum supply chain, where we have two parts, upstream and a downstream part. Until now, the oil products are still one of the major energy sources in the daily life of industries and the people. The lack of these products may lead to disruption in daily activities. So, one of the major challenges in the oil supply chain is the management of the transportation activities of petroleum products from the refinery to the centers. In the oil industries, the transportation is usually made through diverse modes, such as trains, vessels, and pipeline. In many countries, most parts of the refined products are transported through pipeline, justified by the pipeline is the reliable, safest, and cheapest way of delivering a large volume over long distance. It can operate around the clock. They are not affected by the traffic, neither by the weather. More than no container moves with the cargo, products only move. The multi-products pipeline system has the ability to carry different types of petroleum products. The technique of batching is used, where different batches of products are pumped back to back without any physical separation between different batches that circulate inside the pipeline. The product transfer to the center when there are a quantity enter to the pipeline. Since other products are circulated without any physical, which lead to a degradation of product quality, as shown in the figure, this phenomena represents the major drawback of multi-products pipeline system. The volume of interface depends on several parameters such as the structure of the pipeline, the flow rate of injection, the travel distance, the topography, and the type of adjacent products. At the oil company, most of the planning and scheduling operation in pipeline system are decided by operation managers, based on their past experience or based on ad hoc calculation. The development in the computational tools and optimization technique are attracted more and more the oil company engineers, where any improvement of the process or better usage of the available resources leads to increase in the profits. The scheduling of multi-product pipeline is a complex problem. The main question in this problem is how to make a feasible and efficient batch schedule that meets consumption demand. According to the literature review, the most important characteristic of SMPS problem are the pipeline structure, modeling types, time-space modeling, resolution methods. In the pipeline structure can be divided into categories: straight pipeline system and network pipeline system. The mixed integer linear programming model or mixed integer nonlinear programming model are used to present the optimization schedule of pipeline with a discrete or continuous representation of time problem. Heuristics, discrete event simulation, exact methods, and decomposition methods are used to solve SMPS problem. The selection of the methods, in general, depends on problem size. In our system to study, we have we have a multi-product pipeline. In our system interesting to study, we have a multi-product pipeline links a refinery to multiple storage and full distribution centers in different locations along the pipeline. Each center must meet the demands of its local customer. For that, the refinery injects different batches into the pipeline to satisfy the center's demands. The following major assumptions are used to build our model. Our products move in the pipeline without any physical separation. The volume of interface is determined by the company engineers and depends on type of adjacent products. The notion of possible and forbidden sequence is taken into account. The pipeline should be always full. Our model is a MILP type, where the objective function is to minimize operating costs, considering as pumping cost and contamination cost, subject to many constraints, among them constraints of pumping a new sequence, pipeline operation constraints, constraints of update pipeline content, constraints of center reception from the pipeline, constraints of storage at the centers, delivery constraints. We have constraints of pumping a new sequence responsible for determining the order and duration of batch. Pipeline operation constraints responsible for keeping the pipeline full. Constraints of storage in the centers. The tank level may vary in permitted range. Our model is focused to ensure the delivery of the demands of multi-period horizon at the desired time with no back order. Those are a part of the decision variables using in our model, followed by our proposed model. We used the Algerian multi-product pipeline system to test the validity of our model. In this system, we have the pipeline with a capacity of 10,000 meters cubed. Links a refinery situated in Western Algeria to two storage and full distribution centers. Each one is located in different city. This system ensures the supplies of oil products to western and southwestern regions of Algeria. It can distribute 4 types of products. The length of planning horizon is 1 month, divided into 4 periods. We used software Cplex to code and execute our model. After 3 176 minutes of execution time, we get it, the optimal schedule that minimizes the total operating cost. The optimal sequence of new batches injected inside the pipeline contains 17 new batches. The gated plan contains all the information, helps the operation manager to decide. At the left side of the planning, we mentioned all the information concerning a new sequence, such as start time and duration of injection, the location of products in batch of the sequence. At any new injection, we can know the volume transferred to the centers. The pipeline content is consequently updated more than our model provides the determination of variation. More than our model is able to give the variation of stock level at the centers during the scheduling horizon. As conclude, we are proposing to do the scheduling of multi-products pipeline with a mathematical model based in mixed integral linear programming formulation. The company can use our model as simulation tools to decide about their optimal schedule. Our work can be extended to network pipeline system with many objectives and random demand. Thank you for your listening. I hope this presentation was helpful for you.